Real inspiration for these talks come indeed from a previous life where I was the tech lead for a backend team that developed a digital identity solution. And it was part of a cybersecurity company. And the developers, of course, were all using security. But when I asked them questions about the underlying cryptographic concepts between what they were using, behind what they were using, it wasn't clear for them. And so I thought I would clarify a bit that. And in this talk, I will talk about the basic concepts, namely hashing, encryption, and digital signature. And with a basic understanding of that and this building block, you should be able to understand a lot of the security mechanisms that are used these days. So let's start with hashing. A hashing function is a function that takes data as input and produces a fixed-sized output that is called a digest or a hash. A very important characteristic is that it is a one-way function. There is no way to find back the input from the hash. Another important characteristic is that if you change only a tiny bit of the input, the digest is completely different. In fact, hashing is used to detect if there was a change in the data, and so it can be used to ensure data integrity. Next, we have, well-known algorithms include MD5, which is not secure anymore, and SHA-256, or more precisely SHA-256. And there are also variants with 384 and 512, and that's the output length in bits. So next, we have encryption. Encryption takes plain text as input and transforms it into ciphertext. And decryption is the opposite operation, going from ciphertext to clear text. Now, encryption is characterized by the algorithms and the key or keys that are used. And they come in two flavors. First, we have symmetric encryption, in which the key used for encryption and the key used for decryption are the same. And this one and only key is called the secret key. Now, well-known such algorithm is AES, 128 or 256. Here, the 256 refers to the key size in bits. And if you want to send encrypted data, you notice that both the sender and the receiver must know that secret key. So they could agree beforehand, but most often what needs to happen is that they need to exchange that key on an insecure medium, and there are key exchange mechanisms to do that. And we will talk about that afterwards. The other flavor is asymmetric cryptography, in which the key used for encryption and decryption are different, but they are mathematically related. This is often called public-private key cryptography, and as the name implies, the private key is meant to be kept very secret, and the public key to be widely distributed. Now, with this kind of encryption, if I want to send a message, an encrypted message to Tim, so that he can only read that one, I will encrypt the message using Tim's public key, and then Tim can decrypt the message using his private key, and because he's the only one that owns that key, he is the only one that can decrypt and read the message. One very well-known algorithm there is RSA. We have RSA 124, which is not considered secure anymore, then 248 and 496. Again, the key length in bits, and we see here that it's longer than for symmetric encryption, and that means usually that these algorithms are slower and more resource intensive. Now, previously we used Tim's public key to encrypt, but what if I use my private key to encrypt? Then anybody can decrypt the message because my public key is public. But because I encrypted it with my private key, which I am the only one to own, it proves now that I wrote the message. And so before we had confidentiality, and now we have integrity and authentication. Well, in practice, we saw that asymmetric encryption can be slow, certainly on long messages. So what we do is we first run it through a hashing function, and then we get a fixed short digest, and then we encrypt that using the private key. And in essence, this is what a digital signature is. So let's now see how to verify the signature. Let's make a bit of room, and if I want again to send that message to Tim, I would hash encrypt with my private key, send the clear text message and the signature to Tim. Tim can now use my public key to decrypt the hash. He can also apply the same hashing algorithm to the clear text, compare both, and if that is equal, then it proves that I was the sender of the message, and then the message hasn't been tampered with. This explains the concepts at a high level of RSA signature. It's not 100% accurate. The important thing is to remember that you sign with a private key, and you verify a signature with a public key. Now, there is an attack that can be done on that. Imagine that my evil twin changes the message, generates a pair of keys, and then encrypts the message using his private key, and then sends that over to Tim. And then he can make Tim believe that the key used is my public key. Now, Tim would do the same check and verify that it is OK, and so he would think that the message is coming from me. Well, what we want to do is verify that the public key is mine. And in the real world, when you want to verify something, you can use a certificate. And the certificate tells you who, it tells you what, it tells you the date, and it has a signature on it. So, sorry, I couldn't resist. So we can, thank you. So we can use the same concept in the digital world. No, all is OK. Well, no, because there is a signature on that certificate. So we want to verify the signature. We can use a certificate. Well, but there is a signature on the certificate. So you get the point, and we'll get to that problem a bit later. So we talked about asymmetric encryption, digital signature, or they're related using a pair of keys. This is, in fact, a more general asymmetric cryptography field. And there is a third thing that is very useful, is key exchange. Because we saw that symmetric encryption is resource efficient, but there is a bit of an issue because we need to share the secret. And so can we get the best of both worlds? Well, yeah, that's hybrid encryption, where the encryption is done using a symmetric key, but the symmetric key is shared using asymmetric cryptography. So again, I'll use RSA here as an example. Talking to Tim, I would generate a random secret, encrypt it with Tim's public key, send that over. Tim decrypts it with his private key, and we know are the only two persons knowing the secret. This is usually not the encryption key. The encryption key is using mathematical operation derived from there. And in fact, we can derive multiple keys, and that can be useful sometimes. So now we've seen asymmetric cryptography, and I used RSA in all examples because RSA is very versatile. It does encryption, it does signature, and it does key exchange. There are, however, algorithms that are specialized, for instance, in signature or in key exchange, like Diffie-Hellman and Diffie-Hellman ephemeral. And there are also versions that are using elliptic curve. The logic is the same, the math underneath is a bit different. OK, let's look how this all can fit together in a typical situation of a browser accessing a web page over a server over HTTPS. So that's TLS over HTTP, or HTTP over TLS, sorry. So what do we want with HTTPS? Well, we want, of course, privacy and integrity, and that means an encrypted channel. But the data flowing over there can be any length. So we would like to use symmetric encryption. And as we saw, we still need to share the secret, so we'll have key exchange in place. But we also want to verify that the server you're talking to is really the server that it pretends to be. And so for that, we'll use a certificate. So that means signature and hashing. Let's take a closer look at the certificate from my site. So we can indeed see the who, and that's the domain we're talking to. The what, that's the public key that's included in the certificate. The when, there is a validity period in the certificate. And the signature. Here is the issuer, or the certificate authority, that signed the certificate. But we had that issue that to verify the signature, we need another certificate. So we look at the top, and indeed, we see a hierarchy of certificate. That's the certificate chain. So let's now look at the issuer that signed my certificate. And it's signed by other CA, so let's look at that one. And we see that that one is signed by itself. It's a self-signed certificate. So we reach the top of the hierarchy, of the chain. So we stop there because at some point we need to trust somebody. And that's the root CA, and that's usually a list of CAs that are included in your OS or browser. Now, yesterday, Michaela was showing me my site and saying, hey, is that your site? Because it says something weird. It says that your certificate is not valid. And I say, oh, kind of panic attack. I'm talking about security and certificates, and my certificate is not valid. So I digged a bit, and two things. The Wi-Fi in this museum has a proxy that kind of does weird things. And so it replaces the certificate on the fly, and it's not valid. So if you want to visit my site, don't use the Wi-Fi of the conference. And also, it means that messing around with the TLS tunnel is kind of hard. OK, with that, I'll go over the TLS handshake, which is how everything is established at first. So the latest and recommended version of TLS is 1.3, and it's a bit different from the previous versions. But I've chosen to present you TLS 1.2 because I feel that it makes the different step a bit more explicit. And so here the goal is to see how the concept I presented so far can come together, and it's not to analyze a protocol in detail. So it starts by the client saying hello to the server with a list of algorithms called the cipher suite. The server picks one that it supports and replies to the client with the cipher suite that it picked. And the cipher suite indicates the algorithms that are used for key exchange. Here we have elliptic curve, Diffie-Hellman, ephemeral, because RSA as a key exchange mechanism is not really considered secure anymore. It uses RSA for signature, AES for encryption, and SHA-256 for hashing. The server will also send its certificate. And then, because we're using Diffie-Hellman ephemeral, it generates a new pair of key that is used only for the key exchange. So the server generates a pair of key, sends the public one to the client. It will also sign that packet using the private key that it has that corresponds to the public key in the certificate. And that's a way for the server to prove that it owns the private key, because otherwise anybody can put a certificate on the server and that's it. OK. Next. The client has received all the information it needs from the server to know which key exchange protocol to use. And so it will, from its side, generate a pair of keys and send the public one to the server. The client now wants to validate the certificate that it received from the server. It validates both the signature of the certificate using the CA chain, the validity, etc. And as I previously said, it will validate that the server owns the private key by verifying the signature that was in the previous packet. No, because it has all the information. It can now generate the symmetric encryption keys. It does that with its private key that it generated for key exchange and the public key generated for key exchange that it received from the server. It has encryption keys, so it can encrypt a packet that is saying that the handshake is done from the client side. We go again to the server. The server can calculate the encryption key also because it has all the information, and then can encrypt a handshake finish package that it sends to the client. And those handshake finish package allow each party to verify that the handshake was OK for the other side. And finally, we can establish an encrypted tunnel, which is encrypted using symmetric encryption. And in fact, we can do both. So there is one in each direction, each having their own encryption key. Now, I showed you one example of how the basic concepts come together with the TLS protocol, but there are other security mechanisms that use the same concepts, and Oliver in the next talk will show some use of that. Now, if you want to go further on that topic, I will be presenting a long version of this talk at Do iOS in Amsterdam later in November, where I will hopefully show a bit of Swift code. And with that, I want to thank Tim for giving me the opportunity to present, and thank you for your attention.